Hi everybody, I'm Tan Qian Hao and today I'll be presenting to you on my research on topology and geometry of three-band models. So my research is in the field of topological physics, which has recently become of interest because of its possible applications to quantum computing and string theory. So what is topological physics? First, let's introduce the concept of curvature. How do you detect curvature of a sphere? You take a vector and you parallel transport it in a closed loop. When the vector has returned to its original point, you have observed that the vector has rotated, and this is due to the curvature of the sphere. Mathematically, this is known as holonomy of a connection. Now, can quantum states have a form of curvature as well? Yes, they can. This is known as Berry curvature. If you adiabatically transport a quantum state in a loop in parameter space, then when it returns to its original point in parameter space, the quantum state will have picked up a phase. This is known as the Berry phase, and is similar to the rotation of the vector. Now, if you shrink this loop down to an infinitesimal point, then you calculate a quantity called Berry curvature. Now, how is Berry curvature related to topology? If you take the integral of Berry curvature over the Brillouin zone in the sense of condensed matter physics, then you obtain something known as a Chern number. This means that every single quantum state can be characterized by this Chern number, which is a winding number of sorts. For two-band models, this winding number counts the number of times the map from the torus to the two-sphere wraps around the origin. Now my research deals with investigating Berry curvature uniformity with the Majorana stellar representation. We are interested in condensed matter models with non-trivial Chern number that has a relatively uniform Berry curvature. One such model is found in my mentor's paper, and this 3x3 Hamiltonian matrix, when I calculate the Berry curvature of this model, I get the following graph. The calculation was done in Mathematica, and you can see that the Berry curvature is relatively uniform. Berry curvature that is uniform tends to lead to better behavior of fractional Chern insulators, and hence it is the goal of my research to understand why these models have uniform Berry curvature. Now, how do I understand Berry curvature uniformity? I try to use the technique known as Majorana stellar representation. This is a way of decomposing higher spin states into multiple copies of spin half states. Now, essentially, I'm trying to find a formula for Berry curvature in terms of the Majorana stars. So one example is for the two-band model, how I can decompose. So for the two-band model, there's a very nice representation of two-band quantum states on the Bloch sphere. However, for three-band models, there's no such nice representation, and one has to employ the Majorana stellar representation to break this three-band model down into two copies of two-band models. Now, why do I want to do this? It is because for the two-band model, the Berry curvature has a very nice geometrical interpretation on the Bloch sphere. The Berry curvature of a two-band model is simply the solid angle on the Bloch sphere. I hope to develop a formula or a form of intuition to understand the Berry curvature of three-band models using the Majorana stellar representation. Now, so what are the results? So I've discovered a new formula for Berry curvature of three-band models, and this formula is shown on the right here. You can see that the Berry curvature is made out of four terms: T1, T2, T3, and T4. T1 and T2 have a very nice geometrical picture identical to that of two-band models, where A and B are the two Majorana stars. T3 and T4 are cross terms between the stars, and I have not found a nice geometrical picture for them yet, although that is on the way. So if I go ahead and plot these four terms, I get figure 8, figure 9, figure 10, and figure 11. Now summing these four terms up, I obtain figure 12, and you can see that comparing it with the other formula, the original formula, I've numerically verified that my formula works for one particular model. And this is numerical verification of my formula. Now, what is of interest is these divergences. So if we look at T1, T2, and T3, we observe that near certain points, near 0.42 pi's, there are these points that have divergences in them. So we wanted to understand why these divergences exist. And why do we want to do so? It's because we see that T1, T2, and T3 all have these divergences. However, when we add T1 and T2 and T3 up, all the divergences cancel perfectly, resulting in this fairly uniform Berry curvature, this non-divergent Berry curvature. So if we want to understand why the Berry curvature can be so uniform, we certainly have to understand at least why the Berry curvature is non-divergent. So the first step is to understand the source of these divergences, and then the second step is to understand why these divergences cancel so perfectly. And then from then, we can continue to try to understand why the overall Berry curvature is quite uniform. So in order to do so, I investigated the discriminant of in the Majorana stellar representation, which is in terms of the eigenstates, the eigen components of the eigenstate, the three-band eigenstate. And this discriminant function here near the k0 points, they can be approximated as this function. Now plugging this analytical expression, this analytical approximation into the terms, into the T1, T2, and T3 terms, I observe I decompose them into a sum of the wedge products of the real and imaginary components of the stereographically projected block sphere. Using this, I investigated the terms with non-zero coefficients, namely this one, this one, this one, and this one. Then I observed that they have three types of divergences. So tabulating the three divergences in a table, they certainly should cancel out, and indeed I have analytically verified that they do indeed cancel out. So there's perfect cancellation of the three divergences, and through an analytical manipulation, I have understood why the divergences here exist for T1, T2, and T3, as well as why they cancel perfectly. And that is the main result for my research this year. Now for a future year, for what I'm working on currently to further the project, is something called exceptional points. So it's observed that where the points where the discriminant is equal to 0, it corresponds to the branch points of the square root function in complex analysis. So these, in physics, they are known as exceptional points, and they have appeared in optics. And so some possible avenues of investigation is the different winding numbers of this discriminant at the exceptional points, and possibly how they impact the divergences. And what is interesting to note here is that according to these calculations, the three-band Hermitian models do not immediately have the exceptional points in their eigenenergy spectrum because of the fact that they're Hermitian. However, and only non-Hermitian systems can possess exceptional points in their eigenenergy spectrum. However, their Majorana stellar representation does in fact contain exceptional points, because their MSR decomposition, they break down into two band models which are non-Hermitian. These exceptional points can possibly give rise to a topological characterization of three-band models, which is definitely a goal of the research, and possibly involve complex analysis or even complex geometry. So that is for the future direction. I hope you have enjoyed this presentation, and feel free to ask me if you have more questions. Bye.